Hello, welcome back. In this part, we will discuss the design steps that we will follow to design the laterally supported beam. So, in the first step, first of all, we will calculate the loads acting on the beam, and we will apply the appropriate partial load factor so that we can find out them as a factored load. And after that, we will find out the factored bending moment and shear force along the length of the beam, and then we will choose a trial plastic section for the beam, which will be worked out from the equation. So this is the equation to worked out. So using this formula, we will find out the plastic section modulus. MD, well, this MD actually will be the maximum bending moment here. This is not actually MD, this will be M, maximum bending moment as M. So we will be using M value here upon Fy by gamma M naught. Gamma M naught is the partial safety factor, Fy is the yield strength. So putting M value here, and then we will find out the ZP. Now based on this ZP value, then we will choose a trial section. A suitable section will be selected which has plastic section modulus greater than the value calculated in the step 3. And we can choose ISMB, ISLB, ISWB, even ISHB. Generally, we can prefer that. So based on that ZP value, we will choose. Now, next step would be to classify our section, whether our chosen section is plastic, compact, or semi-compact, that we will classify. Now, based on the table 2, using table 2, we will classify, and this classification is based on the ratio B into TF and D into TW. B is the width of flange, T is the thickness of flange. Similarly, D is the depth of flange, and TW is the D is the depth of web, and TW is the thickness of web. So we will find out these two ratio, and then we will compare these two ratio using the table 2. And based on that, we will classify whether our section is plastic, compact, or semi-compact. So that we'll do when we will be solving the problem. So that is the step 5. Now, in the step 6, we will find out the design shear strength, VD. So by using this relation, so I have already discussed about the design shear strength. So using this relation, we will find out VD value. And then in the 7th step, we will check whether our beam is of high shear or low shear. If the V value, V is the factored shear force, which we have calculated in step 2. So we will compare this. If V value is less than 0.6 times of VD, then we will say that our beam is of low shear, is experiencing low shear value. If the value of V is more than 0.6 times of VD, then we say that beam is of high shear value. So based on these two cases, we can find out the strength of bending strength of beam. So as in the next step, we will find out the design bending strength based on the case whether V is less than 0.6 times of VD, or V is greater than 0.6 times of VD. So based on this criteria, we will find out the design bending strength. Now, if it is a low shear, then simply we can find out the MD value using this relation, and then we will satisfy this with the respective condition whether our beam is simply supported or cantilever. So based on that, we will satisfy the MD value with the respective formula. If it is of high shear, in that case, we will find out the MDV value, and then we will compare after, if it is high shear, then we will find out the MDV value by using the respective values. And again, the value of MDV should be less than this 1.2 times of ZE Fy upon gamma M naught. And this formula is for the plastic and compact section, and this value is for the semi-compact section. Now, if the maximum bending moment that we have calculated in step 2, if it is more than the design strength that we have calculated, then what we will do is we have to increase the section size, because in that scenario our beam is not suitable to support the required load. So in that case what we will do is we have to repeat the design, and this time we have to increase the section size and then repeat from step 5. Similarly, if the design shear strength is less than factored shear force, in that case also we have to redesign the section by increasing the section size. So in both scenario, if design bending strength is less than maximum bending moment, or factored shear force is less than design shear force, in both case we have to redesign our problem. Then once we are satisfied with the step 8 and 9, then we will check our beam for the deflection criteria as per table 6. Then in the 11th step, we will check our beam for the web buckling criteria. Now, first of all, we will find out the ratio D by TW. D is the depth of web, TW is the thickness of web. If it is less than 67 times of epsilon, epsilon is called basically the yield stress ratio, and this is actually 1. Normally it is 1. So in that case, we will assume that web is safe in web buckling, and there is no need to check web for the web buckling. But there is a condition: by chance, if our beam is of high shear case, in that case we are supposed to check our beam for web buckling criteria, and web buckling formula is AB into FCD. Well, I have explained this earlier also, so this there we will see again. So AB is the area of web at the neutral axis, which is actually B1 plus N1 in case of support, and B1 plus 2N1 in case of below the concentrated load. So this B is actually this one, depending on the case, and we will multiply this by the FCD. So FCD can be calculated once we find out the slenderness ratio using the table 9C. Now, buckling strength should be greater than the design shear force. Okay, so that is the, I mean, factored shear force. Buckling strength should be more than that. In that case, we will say that our beam is safe in buckling criteria. Similarly, after the last step would be to check our beam against the web crippling. So again, as mentioned in the step 1, the web crippling strength should be more than the design shear force. So this is design shear force, which is V, and FWC is the web crippling strength. So again, for our beam to be safe in web crippling criteria, it should be more than the design shear force. So these are the steps that we are going to follow while designing the problem. So in the next lecture, we will design a problem based on steel beam, based on laterally supported criteria. Thank you.